Okay, so we're now going to get into the proper contents of the course. Um, so what is logic? Okay, so logic has a very long history, um, and it overlaps with philosophy quite a bit, going back to Plato. But for our purposes, logic is just going to be a formal system for determining if a statement is true or false. So we're going to start off with Tarski's, Alfred Tarski. So Alfred Tarski. He was a logician, mathematician, philosopher, and he gave the following criteria for determining when a statement was true. So the statement P is true just in case P. Okay, so that seems like a very weird thing to say, right? The statement P is true just in case P, but if we replace it with an actual statement, um, it'll make more sense. So how about instead of P, we say Paris, so say P is equal to Paris is in England. Okay, so this is the first example from our text. So the statement Paris is in England, right? This is true just in case, in fact, Paris is in England. So one way to think about this general formula, this general approach to evaluating statements, is that the statement over here in the quotation marks, this is a formal statement. It's just characters, just words, right? Whereas this thing on the right, this is about the world, right? And so we can call this the correspondence principle. Okay, and I believe Aquinas talks about this at some point, though I'm not familiar with his work very well. But yeah, so it goes back to Aquinas, and then recently with Tarski and a whole bunch of other philosophers. Okay, so now that we've got that out of the way, for our purposes, we're just going to just interchangeably use the P with quotation marks or without it, and we're not really going to think too much about it just because we have that correspondence principle. Okay, so a statement is something that is true or false. So a statement is something true or false, but not both, and definitely not neither. Okay, so we're often going to use letters like P, Q, and R. And the truth or falsity of a statement is called its truth value. So the truth value it is true or false. Okay. True or false. Okay, so to keep touching on the philosophy just a little bit, we could say that P and Q and R, or the statements that these letters represent, the statements are called truth bearers. Okay, so statements are truth bears and facts of the world are truth makers. Right? So what is it that makes Paris is in England false? Well, the truth maker, right? Namely the fact that Paris is in France, right? So the fact that Paris is in France makes the statement Paris is in France true. And since France does not equal England, it would follow that the statement Paris is in England is false. Okay, our second example is 2 plus 2 equals 4. Okay, so this is a true statement, right? Under the usual interpretation of plus and 2 and 4. Under the usual interpretation, 2 plus 2 is a true statement. So, again, strictly speaking, we don't want to say 2 plus 2 equals 4 is true. Rather, it would technically be the statement 2 plus 2 equals 4 is true, right? And why is it true? Because 2 plus 2 equals 4, right? And if you wanted to, explain why 2 plus 2 equals 4, then you'd have to get into some mathematics, like the proper study of mathematics, right? Okay, so there are a few other examples here. One of them is, where are you going? So where are you going, right? Where are you going? Where are you going? Right? And so that's a question. And then you have put the homework on the blackboard. Put the homework on the blackboard. And this is what we call an imperative. Okay, and then you can say other things like, let's see, this pillow is comfortable, or the sweater is comfortable. This sweater. Okay, so where are you going? Okay, so does that have a truth value? Well, no, it doesn't, right? Because there isn't a statement of fact, right? It's not you are going to the store, or you're going to bed, or whatever. It's just, where are you going? It's a question. So there isn't a way to make this true or false. Now, if we give an answer, then the facts of the matter are going to make that true or false. But just as a question, it's not really true or false. Okay, so the next one isn't true or false either, because it's just put the homework on the blackboard, right? That's a command. So, if I tell you to do something, it doesn't have to be true or false, right? So it's not as if everything can be viewed through the lens of logic, right? There are some things, some forms of communication that we use that are just statements of opinion or commands or feelings, right? And that gets to this next sentence, which is the sweater. This sweater is comfortable. So I guess from the subject's point of view, you could say it's true or false, but is it a fact about the world? Maybe, maybe not, but I guess that's veering more into philosophy. Okay, so now that we have that out of the way, many of our statements can be broken down into simpler statements. So let's see. So you could say, I am a student at UST, and my major is philosophy, right? So this statement is going to be true just in case, right? Just in case. So the whole statement is going to be true just in case. The first part, I am a student at UST, and the second part, my major is philosophy, just in case both of those statements are true. So if either one of them is false, the whole thing is false. But the key I want you to get right now is that we can, I guess, well, I'll have to figure that out later. So the key here is that I can break this up into essentially two parts, right? And we could just evaluate those separately. So earlier I used the letter P or Q to represent an entire statement. But if this whole thing is P, right? If this whole thing is P, then I could say, that's R and this is Q. Okay? The choice of, that's a terrible Q, it looks like a G. Q, right? Okay, so in this case, we would say that P equals Q and R. Okay? And now we're going to get into the general logical connections. So there's really, you only really need two, okay? But practically we're going to use like 4 or 5 different logical connections. Okay, so you have and, you have or, you have not, and you have implies, and the symbol that we use for and is this little caret symbol. For or, we flip that, so it kind of looks like a V, but not quite. For not, we use a tilde or a minus sign or a little hooked thing like that. And then for implies, we use an arrow. Sometimes you also see this little horseshoe sort of looking thing. Okay. And these symbols, these are called the logical connectives. And they're the logical connectives for first order logic, which we'll abbreviate as FOL, FOL. And at this point, we're not going to use quantifiers. So what I mean by a quantifier, I mean a statement that is about a collection of stuff, right? but we'll get to that later, or most likely, actually, we won't. Okay, so we're going to go through each of these bit by bit, and I'm going to try to clarify what all of them actually mean. Okay, so and, right? Right. So and, it's true just in case both parts of a statement are true. So A and B, and also sometimes instead of that, sometimes we also use the the and symbol, right? But A and B is true if and only if. So if and only if, I'll abbreviate that as IFF, and I'll tell you what that means in a second. So A and B is true if and only if A is true and B is true. Okay, so if and only if means that this whole side of this whole side of, so looking at this whole statement, right? This whole thing right here, this whole thing right here, this whole sentence. If this side is true, then this side is true. And I'm not talking about true in the sense of this statement being true. I actually mean this thing being true. Okay, so if it's true that A and B is true, then A is true and B is true. Okay, that's probably a little confusing, but that's just how it is. And then conversely, if it is true that A is true and B is true, then A and B, then it is true that A and B is true. Therefore, A and B is true. Okay. Another way of looking at it, this if and only if statement, it just means that the two statements on the left and the right, they're equivalent. So we can interchange them. Okay, so often we like to teach these concepts using Venn diagrams. So if I have let's say here is A and here is B, right? Then A and B is what they have in common, right? So this is A and B. So I actually just used a little, it's called a cap, right? It also looks like a horseshoe. We often call it the cap. And this is more for set theory, but the idea is very similar. So if you look at a collection of things that have the property of A-ness and B-ness, then they'll have A and B-ness, right? So let's see. So yeah, so the example I gave a second ago about being a student at St. Thomas and being a philosophy major, it's only true if you're both a philosophy major and a student. If either part is false, the whole statement is false, right? So if you're a philosophy student at, let's say, Dartmouth, right, Dartmouth, then it would be false that you are a student at St. Thomas and a philosophy major, right? Okay, yeah, pretty straightforward. What's more interesting, perhaps, is the fact that right, and but are equivalent. Okay, so and but are equivalent. And what I mean by that is that from a facts point of view, they are equivalent. What do I mean by that? Well, let's look at some statements. So the book has some good examples. It says, Mark is poor but happy. So Mark is poor but happy. Okay, so the question is, how is this any different than saying Mark is poor and happy? And it's not all that clear what the difference is, right? At least from a first order logic perspective. So there is something to this but, right? So the idea is that but it's kind of negating a subjective experience, right? So both of these are true, right? Mark is poor and he is happy, right? So the fact that Mark is poor but happy makes him both poor and happy, right? And so by the definition I gave just a moment ago, because he's both poor and happy, Mark is poor and happy. Okay, so what's up with this but? Well, as a society, we've, we attach meaning to stuff, right? So we're putting, a negative opinion on being poor, and we're putting a positive feeling on being happy. And so the but is just used in everyday conversation to show a contrast, right? That's all that is. So anytime you see but, you can just replace it with and. Okay, so not there's no need to go over that anymore. I think we got it. Or now this one tends to confuse people. So again, or is often in everyday language. It's often used what in a way that we would call the exclusive or, right? So we put an X in front of it. So that's the exclusive or, right? So how would we normally use this? We'd say something like, you can have pick A or B, Tim, right? And let's say Tim's dad tells Tim that he can have a PlayStation or a swing set, so, something for Christmas, right? Tim isn't going to say, well, Tim actually might say, I'd like both. But what does Tim's father really mean? He says, pick A or B, Tim. And then sort of tacitly in the background, he's saying, but not both, right? But not both. Okay? And we sort of intuitively know that, right? It's a social norm that when we use or, this is often what we mean when we say or. But for our purposes, we're not going to use this, right? So for us, or is not the exclusive or, but rather it's the inclusive or. So how does this work? So A or B, right, is true if at least one of A or B is true, or possibly both, right? So yeah, so like A could be study hard or go to sleep, right? And if you study hard and you go to sleep, then the statement John studied hard or went to sleep, it's true, right? So suppose John studied very hard. Let's say he studied 5 hours. Let's say John studied at least 5 hours or went to sleep. Let's say he studied for 5 hours and then he went to sleep. Then the statement John studied 5 hours or slept right? This is true, right? Because he did at least one of them. So in fact, he could do both, right? How would it be false? It would be false if John did not study at least 5 hours and he did not sleep, right? So just imagine John is, he just can't sleep because he's worried about his test, but he just doesn't. He just decides not to study. He just gets really anxious and I don't know, watches YouTube videos all night. Okay, so going back to our Venn diagram, if this is A and this is B, again, what's this area in the middle? That's A and B, right? But what is OR? Well, OR is going to be all of it, right? So that shaded region is A or B. Now this is where students often get tripped up, right? Because it looks like it's A and B, right? And that's correct, right? Either all of A and B make up A or B, but it's not what elements make up A or B that we're concerned about. It's what things make it true, right? And that's what you need to keep in mind. So a statement A and B is true just in case it is true of both. Whereas as long as either A or B is satisfied, the whole statement A or B is satisfied. And so that's why that's why this works the way it does. Okay, so now we're going to go to not. Okay, so how does not work? Well, not is basically the negation. Okay, so it's going to take a statement and make it true just in case it is false, right? So not P is true just in case P is false. Okay, again, this isn't how you would normally talk, right? You don't say not 2 plus 2 equals 4, right? This is just, this is a logical language, okay? I mean, I suppose, like, when you're a kid, sometimes you say something and then at the end you exclaim, not, but that's not exactly the same thing. Okay, so here's an interesting corollary of this definition. So what does not P, what is that equivalent to? Not P. Okay, Well, that is, so that's a triple equal sign, by the way. That's just another way to say equivalent to. This is equivalent to P, right? And let's think about it. So if this whole thing was, say, Q, then not Q is true just in case not P or Q is false, right? And so when is not P false? Well, looking at this definition, since something is either true or false, not both, and has to be at least one, then if not P is false, then P has to be true, right? So if you have not P, then not P is true just in case P is true. Conversely, not P is false just in case not P is true, and not P is true just in case P is false. So again, not P is false would mean that P is false. Not P is true implies that P is true. Because the two agree on their truth values, the two are logically equivalent. Okay. So we're going to use this triple equal sign to mean that two things are logically equivalent. And two statements are going to be logically equivalent when they have the same truth tables. So we haven't quite got to truth tables, but we're going to get to that in just a minute. Okay, so the Venn diagram that you can think of is actually, it would be the complement. So if this is your A, right, then this would be not A, right? Where the rest of the screen, you can just pretend it doesn't exist, right? So so all these Venn diagrams are always relative to some universe of discourse. So for example, if it was the numbers less than or equal to 3, right, and then we took the naught of it, right, then that would mean it's a number greater than 3, right? So this means that x is greater than 3, right? So if it's not the case that x is less than or equal to 3, then x is greater than 3. Let's do some other example. How about it's not the case that 2 plus 3 equals 5, right? What would that mean, right? Well, it would mean that 2 plus 3 does not equal 5. I didn't say that these statements were true. I'm just saying that's how we would evaluate it. Obviously, 2 plus 3 is equal to 5, but we're allowed to write down things that aren't true, right? It's not hurting anyone. Okay, so the next thing we're going to get to is implication. And it also goes by the name material implication. Okay, so this is basically our implies statement. So I've used that word kind of loose, and I was making statements about the theory of logic, but this is inside the theory of logic. Okay, so what do I mean by that? Well, what I mean is that the statement A implies B, this is going to be true, right, under certain conditions, right? And I said you could also use the horseshoe thing. It's shaped like that, kind of, right? But we're not going to do that. Okay, so when is this true? So this is true just in case either A is true, sorry, A is false, or B is true, right? Or both. So this is when it's true. So how could it possibly be false, right? Well, the only way it could be false would be if A was true and B was false, right? Because if A is true and B is false, then it's not the case that A is false or B is true. Okay? So, yeah, there's a lot to unpack what I just said. So, and there's also a lot of funny things you can do with material implication. You can say things that are true that kind of sound funny. But let's first talk about the truth table. Okay, so first off, A implies B. This is logically equivalent to not, right? So I can use the word not. I can write it big like that, or I can use the little hook thing. So earlier when I said not P, right? When I said not P, I said that was equal to P. I can also do hook P equals P. Same thing. But I'm getting off topic. I'm sorry about that. Right, so A implies B. This is equivalent to not A or B, right? And the reason is because we can draw a truth table. So this is a good introduction to truth tables. So the way truth tables work is you put your variables, your atomic variables, up here, A and B, and then you have your compound statement at the end, like A implies B, and you go through the different combinations, right? So how many combinations are there for A and B? Well, there's 4, right? Because you could have A be true and B be true. And you could have A be true with B false, right? And you could have A be false and B be true, or you could have them both be false, right? They could both be false. So what did I say? Well, I said that this would be true just in case either A is false or B is true. So right here we have that A is false. So this is going to be true. And it's going to be true regardless what I put here, right? Because that's the rule, right? If A is false, A implies B is true. So this is also going to be true. And it doesn't matter that this is true or that this is false. The antecedent is true. So the first half of this we call the antecedent. The thing on the right we call the consequent. Okay, the other condition under which this is true is when B is true. So this is true. And so that leaves us with this case, right? So this is when it's false, right? So let's go ahead and compare this to, I guess we could add not A, and then we could add not A or B. Okay? And we're going to compare this right here with this. Okay, I'm going to show that they're actually the same thing, and that's why we're going to say they're logically equivalent. Okay, so here, these two first columns, these are the inputs, and you could think of everything to the right is different outputs, right? Okay, so what's not A? Well, if A is true, then not A is false, right? So that's false, and now this is true because A was false, right? Okay, not A or B. So that, remember, you can put a bracket around it. So that's the way you would read it. The not symbol, it has precedence, you could say. So it's more tightly bound to A than the or symbol. This is like the order of operations that you learn for like multiplication, addition, and so on. There's also a order of operations with logical operators. So usually we don't put those parentheses there, but I just put it there just to, help you. But in the future, I'll typically only use them if it's more complicated. Okay, so this is going to be true if at least one of these is true, right? So is B true? Yeah, B is true, so the whole thing is true. Okay. Okay, what about this? B is false, so maybe this is false. But not A is also false. So not A, right? We have not A, and it's false, and B is false. So the whole thing is false because neither of them is true, right? Let's see. Not A, it's true, right? So this whole thing is true. And again, this is true. So, I mean, if you just compare these two columns, right? Because they're identical, this is how we know that A implies B is logically equivalent to not A implies B. Now, to be fair, I did define A implies B to be that particular statement that is true just in this particular, just under these conditions, right? The ones I just circled, right? So it's kind of like we defined it in a way that just so happens to coincide exactly with not A or B, and then sort of after the fact we say, oh hey, they're actually equivalent. Okay. So here's some funny statements. Let's see. Let's see. If I am a millionaire, then I am the Queen of England. Right? So I'm in fact not a millionaire, right? I'm not, sadly. And because I'm not a millionaire, the whole statement is true, right? So the whole statement is true. And somehow this kind of violates our intuition, right? And so in the philosophy of language, this is one of those ongoing things they talk about. How should material implication work? Because it you get these funny statements, but actually it does have a lot of more natural settings where it seems to work. But the implication, the if-then sort of statements, they don't quite work in first-order logic, which is what we're doing. So how would I write this in logic, well, basically the if part, right, if I put that in parentheses, right, the I am a millionaire, that would be P, right? And the I am the Queen of England, that would be Q. And then this whole thing would be P implies Q, right? P implies Q. So P is I am a millionaire, and Q is I am the Queen of England. So the if and the then is kind of programmed into the arrow. So the arrow is kind of equivalent to, you have something here and you have something here, right? Some, inputs. And so this, you could put like a star and then like a double star, right? And this would be like if star, then double star, right? Now, on a personal note, I think that the more correct way to think of if-then statements is not the way that we're teaching it in class. I think it's actually more proper to think of it as a modal statement, right? But we're not going to get into modal statements in this class, and so modal logic is basically about the logic of possibility. And so somehow, even if I were to become a millionaire, I could not be the Queen of England for a number of reasons, right? I don't have the lineage, and also I'm not a woman, so I couldn't possibly be a queen. But anyway, and more importantly, I'm not English, or I don't have any related lineage to that family. So somehow, even though this statement is true currently, it would it would become false if I became a millionaire. But somehow, this ordinary logic just does not capture that. So. Okay, so that's it for the intro to logic, and in the next video, we're going to cover some more topics on propositions and truth values.